This can be kind of confusing to keep track of because there are two different quantities known as electric potential and electric potential energy. So potential energy, two different things. Okay, potential is the variable V, and that's, if you know the voltage of an outlet, uh, that is the electric potential. Potential energy will typically use U. I know we've used PE for other stuff, but we'll typically use U. Uh, and this says as I said, this has units of volts. This has unit of joules. It is in energy, and they're related, and I'll explain how they're related. But I want to make sure that you are clear that these are two separate quantities. Potential is one thing. Potential energy is something different. All right. Now, going back way back to last semester, we learned that work was F cosine theta times D, right? So we're going to consider the work done as we've got an E field pointing to the right, and we're going to consider the work done as we move a positive charge to the left. And this is very similar to, in concept to the work we would do if we took an object and raised it against the gravitational field. So we originally said that back in the day that work was equal to the net work was equal to change in kinetic energy, and this work could be done by non-conservative forces or it could be done by conservative forces. And then the conservative forces we wound up moving over to the other side, and that's how we got spring potential energy and gravitational potential energy. Right? And this is how we get electric potential energy as well. We know that work is force times distance, so the work done as we move this charge, we'll call it Q naught. The force on this charge we know is the electric field times Q naught. And that work is going to be negative because we're applying a force, or the work done by the electric force is going to be negative because the field is pointing in the direction opposite the displacement, which means that the force is pointing in the direction opposite of the displacement. There's a negative, and that actually, or you could think of it as being cosine 180, and that's where the negative comes from. And then the distance is just there. So work is QED. But then, that starts out on this side, so when we move it over, we define our electric potential energy, which we use U for, to be Q naught E times D, and it's positive because it gets moved over to the other side of this equation. All right. So this is our electric potential energy. Now, because there's this value of Q here, it's useful to define the potential is potential energy per unit charge. Oops. Okay, so a change in potential is equal to a change in potential energy over that charge. And the unit, I said it was volts, it's 1 joule per coulomb equals 1 volt, capital V. Right? So this is actually somewhat sensible. The variable is V and the unit is also V, so that's fairly easy to keep track of. Just like with potential energy, we know that we could set, for gravitational potential energy, for example, we could set our zero wherever we wanted to, and everything would work out okay. For potential also has an arbitrary zero. All that matters physically is a change in electric potential, and so we can set the zero wherever we want. And there's typically the zero, where we set the zero depends on what the charge distribution is. There's another common unit of energy used in physics that kind of comes out of this sort of formula. We know Q naught times delta V is equal to a change in U just by rearranging this equation right here. And the unit is defined for a potential difference of 1 volt for an electron or proton moving through a potential difference of 1 volt. And this gives us a 1.6 times 10 to the minus 19th joules, and that is the unit that is referred to as 1 electron volt. So that's the conversion to that separate unit. An electron volt is a unit of energy equal to 1.6 times 10 to the minus 19th joules. The reason they use that energy is largely due to, in atomic physics, the numbers are, on the order of 10 to the 19th, 10 to the 18th, really small numbers of joules, and so it's handy to have this much smaller unit so that we can give more convenient numbers. And we'll use electron volts a lot when we do atomic physics in particular. The definition of potential and potential energy actually gives us another way to think about the electric field. We know that our delta U, our change in potential energy, is our potential energy is Q naught E times the distance. It's actually a displacement, which is often referred to as delta S as a vector. So this is basically just the same thing as distance. It's just S is typically used for a displacement vector. And so a change in U, this should be times S, is equal to Q naught E delta S. And if we define delta S to be positive in the same direction as the E field, then we have to throw a minus out front here. So this is for a displacement going against the E field, but it makes more sense that if the electric field, it makes more sense to do it this way, because if the electric field and the displacement are in the same direction, that is a decrease in potential energy. So that's why we define our change in potential energy this way. Now we know our delta V is equal to delta U over Q naught, which gives us that delta V is equal to minus E times delta S, or that the electric field is equal to negative change in potential over the displacement. In reality, this is a derivative. So the electric field is the derivative of potential with respect to displacement or distance. And it's a voltage over a displacement, so that unit then is a volt per meter. But remember, a volt was a joule per coulomb, and a joule is a Newton meter. So you can see that's equivalent to newtons per coulomb. Volt per meter, Newton per coulomb, they're the same thing, and both are viable units for the electric field. So if we consider this relationship, if we consider an analogy to gravitational stuff, the electric field, the potential is the height of your hill, like it's how high up you are on the hill, while the electric field is the slope of the hill. Yep. So that's a way we can give the analogy to gravity. Here's a quick concept sort of question. I recommend pausing and thinking about it after I say it. So if for a given area the potential is positive and constant, what can you say about the electric field? What can be said about the electric field in a region where the potential is positive and constant? Think about that for a second. Well, we know electric field is change in potential per distance. So if it's constant, there's a relationship here where if the potential is constant, that means that the electric field is 0. So keep in mind that relationship, that a change in potential leads to an electric field, and an electric field means a change in potential.